All aboard! The 8mm camera troubleshooting exploration is about to depart. Tape 2 of this program covers everything from how to check out the different parts of the camera section to the circuits involved in camera processing. Before troubleshooting actually begins, take a moment to first inspect the lens assembly for physical damage. Also manually turn the zoom and focus assembly to see if there is any mechanical binding. Both the zoom and focus components are most prone to physical damage in the camera section. If the lens does not bind, hook up the camcorder to a color monitor, an oscilloscope, and a vector scope, and continue with troubleshooting. Our first stop in troubleshooting the camera section is to see if the unit will power on. Apply main power to the camcorder. Place the power switch to the camera position. Also, place the Start-Stop button on the hand grip to standby. Confirm that there is a picture in both the monitor and the viewfinder. In addition, you will also see a rectangular window in the viewfinder indicating that the autofocus mode is on. Mechanically, the focus lens should turn and the zoom ring should function when the zoom button is pressed. In this second scenario, if the camera does not power on, the problem is in the system control or power supply. The CCD F33 utilizes a DC to DC converter to power both the camera and VTR sections. In Sony camcorders, both the camera and VTR are activated in the camera mode. However, in the VTR mode, only the VTR section is on. The voltages necessary to operate the VTR section are regulated 5 volts DC, video 5 volts DC, and audio 5 volts DC. The voltages necessary to operate the camera section are 32 volts DC, 15 volts DC, and 5 volts DC. Refer to the service manual schematic or block diagram for the source of these voltages. When the camera or VTR is powered on, the capstan and drum servo motors always receive power directly from the main battery. The rest of the camcorder receives power from the DC to DC converter controlled by system control. When the VTR on button is engaged, system control senses a low at its VTR input switch. System control outputs a VTR on command signal to the DC to DC converter to turn the VTR section on. In a similar manner, if camera power is selected, a low is detected by system control. System control outputs a camera on and a VTR on command signal to the DC to DC converter. This powers on both the camera and the VTR sections of the camcorder. Once powered up, system control communicates with the camera DDS CPU via the internal data bus. This is crucial because without data present, no camera functions operate and no video is output from the camcorder. So when troubleshooting either of these conditions with B+ present, verify that there is data communication taking place between system control and the camera CPU. If the camera does power on and the zoom works, check for proper focus operation. Focus inspection is divided into 3 sections: manual focus check, flange back adjustment and focus ring accuracy, and automatic focus check. For any of these focus checks, mount the camcorder on a tripod and shoot a Siemens star pattern. Position the star pattern exactly 2 meters from the lens focal mark located on the right cabinet of the camcorder. Then install an ND.9 filter over the lens to reduce the illumination, which forces the iris fully open. With the camera in manual focus, set the zoom lever to telephoto and confirm that the Siemens star pattern is centered on the monitor screen. To quickly confirm that you are in the manual focus mode, press the data screen button located at the top of the camcorder. A manual focus symbol should appear at the top center of the monitor with the data screen on. The same display should appear in the viewfinder when manual focus is activated. When automatic focus is disabled, you should be able to position the lens manually. Manually rotate the focusing ring for maximum definition at the center of the Siemens star pattern. Confirm that the focus mark on the lens is at the 2-meter scale mark within 1/16 of an inch. This should be the same distance as the camera from the Siemens star pattern. If it is not, then perform the flange back adjustment as described in the service manual and repeat the previous steps. If the flange back adjustment is correct, check autofocus. Manually rotate the zoom ring to the extreme wide angle at the 7mm scale mark. Turn on the autofocus mode. Confirm that the unit focuses within 2 seconds and that a sharp image is obtained. As a final check, temporarily turn off the autofocus and then rotate the zoom ring to the extreme telephoto mark or 42mm scale. Then turn on autofocus again. Confirm that the image is in focus within 2 seconds and that the image is sharp. If these conditions are satisfied, focus is operating correctly. After determining that all focus modes are functioning, next check the calibration of the camera's auto and preset white balance adjustments. Position the lens focal mark approximately 2 meters from a light box with an all-white pattern. Install a Sony C14 color conversion filter combination or 80A and 82 filters in front of the lens to simulate outdoor light. Note that the filter combination will vary from model to model, so check the service literature for the correct filter. Press the white balance button located on the right cabinet to select the outdoor white balance mode. A sun symbol should appear in the viewfinder and on the monitor if the data screen is on. Using a vector scope, confirm that the center of the white luminance point has moved to the center of the screen. This confirms proper outdoor white balance. Remove the filters previously installed. Then press the white balance button once again to select the indoor white balance mode. To confirm the indoor white balance mode, a light bulb symbol should be displayed in both the viewfinder and on the monitor screen, again with the data screen on. If the white luminance point is at the center of the vector scope screen, indoor white balance is correct. Next, press the white balance button again to select the auto white balance mode. Again, confirm that the center of the white luminance point is in the center of the vector scope screen. If the luminance point shifts away from the center during any mode, recheck the vector scope adjustments and the lightbox calibration before judging that an alignment is required. If the zoom, focus, and white balance modes are functioning, but the image is dark or excessively bright, check the iris. The iris in the lens maintains the amount of light seen by the CCD imager by opening and closing. The iris is opened and closed by a motor which operates against mechanical spring tension. When power is removed from the camera, the spring forces the iris to close. The iris control circuit continuously regulates the amount of light that is permitted to pass to the CCD imager by opening and closing the iris shutter. The signal from the iris control circuit is sent to the iris detector where all video scene brightness levels are averaged. The resulting voltage is sent to the driver for comparison to an external reference voltage. This reference voltage is used to set the standard iris video signal level or camera sensitivity. The reference voltage can be changed using the RM95. Consult the service manual for a detailed description of this adjustment procedure. The result of this voltage comparison is used to drive the iris motor and control the mechanical aperture of the iris. To prove that the iris section works, we have placed a light box with a color bar pattern in front of the camera. As the light level of the light box is varied, observe the iris out signal on the scope. Notice that as the light level is raised, the iris out signal first increases in amplitude and then decreases back to normal as the motor operates to close the iris. As the light level is lowered, the video amplitude decreases, then increases back to normal as the motor operates to open the iris. You can also scope the iris driver output to verify iris drive operation. Check for a change in voltage at the output of the iris driver. The video signal level should also change. If the voltage changes but the video signal level does not, suspect a defect in the iris motor or mechanical binding of the iris assembly. The brightness level of the image is not only controlled by the iris but also by the AGC circuit. The AGC circuit is used to maintain a constant video signal level and ultimately a constant output video signal level from the camera. This is done in spite of the wide signal variations delivered to the AGC circuit by the iris circuit. What sets the AGC stage apart from the iris stage? To begin, in the AGC stage there are no motors to turn and no iris shutters to open and close. And where the iris circuitry maintains a coarse video signal level at the initial stages of the camera, the AGC stage maintains a fine video signal level to all other stages. Let's see how it operates. The pre-video information from the CCD is first sent to the signal separator circuit, then to the AGC amplifier, and then to the matrix circuit. From the AGC amplifier, the signal goes to an AGC detector. The detector serves the same purpose as in the iris circuit, that is, to rectify the various brightness levels of the video signal to an average voltage. The signal then goes to a voltage comparator for comparison to an external voltage reference. The voltage reference sets the standard AGC signal level as in the iris circuit. The AGC output goes to the AGC amplifier and to all other voltage gain-controlled amplifiers in the camera. It raises or lowers all amplifier gains throughout the various camera stages in proportion to the video signal. The actual amount is inversely proportional to the detected signal. That is, the greater the detected signal, the lower the amplifier gain. And the lower the detected signal, the greater the gain. The iris and the AGC circuits work together to correct for varying brightness levels that occur in a normal scene. For this reason, AGC operation should be checked in conjunction with iris operation. To check AGC operation, aim the camera at a light box with a color bar pattern 2 meters from the camera lens focal mark. Connect channel 1 of the scope to the iris outline and channel 2 to the AGC control line. To locate these points, refer to the service manual. Set both channels to 1 volt per division vertical deflection with DC coupling. Take note of the voltage levels for both the iris and AGC. Slowly place an ND1 and ND.4 filter combination over the lens. As the ND filters cover more and more of the lens, the iris voltage should increase to compensate for the reduced light level and to open the iris. When the iris voltage reaches the maximum 4 volts DC, it means that the iris is fully open. This threshold voltage level causes the AGC to increase to provide brightness gain control. This proves that the iris and AGC stages are both working to maintain brightness with reduced light input. When the filters are placed completely over the lens, the AGC increases to its maximum. When the ND filters are removed, both the iris and AGC control voltages should return to their previous voltage levels. A normal scene should reappear within 1 second. If you observe these conditions, the iris and AGC are functioning properly. When the iris and AGC sections are functioning properly, the image may still not be correct. This leads us to the video processing stages. A failure here could cause problems like missing or weak colors, only one video field or extreme color loss, or no white color. These problems will be discussed as we test each stage for input, output, and support signals. The first stage in our video processing analysis is the CCD. The signal output from the CCD consists mostly of a carrier signal. The video signal information occupies the smaller part of the waveform signal. At a higher horizontal time base setting, we can see the video signal clearer. How can we determine that the video signal is really present at the CCD output? Notice that when the lens is capped, the video signal information diminishes and only the carrier signal remains. The diminishing video signal not only proves that the CCD is producing a video signal, but that the iris is open. If no signal is present at all, check the VDD supply voltage, as well as the PG, H1 and H2 and V1 through V4 support signals output from the timing generator circuit to the CCD. If a carrier signal is present but no video signal is detected, then first verify that the iris is open and confirm the presence of the VL signal output from the timing generator before replacing the CCD imager. As we saw earlier, the CCD output signal is sent to the signal separator stage. The signal separator IC separates the smaller video signal from the larger carrier signal with the aid of 3 clamping and 4 sample and hold pulses. Once separated, the signal separator stage outputs 2 encoded color signals on the S1 and S2 lines and the luminance signal on the Y line. When shooting a standard color bar pattern, the S1, S2, and Y waveforms look like this. The camera output video signal appears in the waveform for comparison. Let's now take a closer look at the color bar pattern. The color bar chart consists of 7 distinct vertical color stripes. Each step in the waveforms correspond to a specific color bar stripe. We can identify any one color displayed in the waveform by blocking each of the color stripes on the color bar chart. We can also see that the yellow and white stripes produce the largest S1 and S2 waveform levels. The cyan and green stripes produce the medium waveform levels, and the 3 remaining colors, magenta, red, and blue, produce the smallest waveform levels. If the Y, S1, and S2 waveforms do not look like the ones shown, then the separator stage or their support signals are likely to be at fault. The SHP, CLP0, and CLP1 pulses are vital to the operation of the signal separator circuit, more so than other support signals supplying this same stage. If SHP, CLP0, or CLP1 were missing, there would be low or no video output from the signal separator stage. Missing SP1 or SP2 would also affect the signal separator stage. SP1 causes a loss of luminance with only blue and dark blue bars displayed. If SP2 is missing, it would cause a loss of luminance with only red and black bars displayed. Although the S1 and S2 signals contain the necessary video information to reproduce a color signal, they still need further processing. From the signal separator circuit, the encoded color S1 and S2 signals are sent to the color matrix circuit. The color matrix circuit decodes the S1 and S2 signals using internal adders, subtractors, and an external CCD delay line circuit. As seen on the scope, a complex color signal from the adders and subtractors is routed to the external CCD delay line. Here it is combined with 2 external delay pulses and 1 clamping pulse. If XDL1 or XDL2 are missing, the colors will appear pale and only 1 field of video will be output. Once combined, the CCD delay line returns a 1H and a 2H delayed color signal to the color matrix stage. The color matrix stage outputs separate RGB signals and a DC reference voltage to the color processor circuit. The DC reference voltage represents the RGB signal's DC level, or simply its black signal reference. The reference voltage also biases the initial stages within the next color processing stage. In this camcorder, this voltage is normally 1.8 volts DC. If this DC reference is not output from the color matrix stage, there will be no color output from the following color processing stage. Within the color processor stage, the RGB signals are used to generate the NTSC R-Y and B-Y color signal information and to white balance the picture with the aid of support signals from the Auto White Balance CPU and EVR IC. When the output of the color processor stage is plotted on a vector scope, the R-Y signal corresponds to the vertical axis information and the B-Y signal to the horizontal axis information. All 7 colors contained in the color bar pattern are displayed around the circumference of the vector scope screen as dots. The distance of the color dots from the center of the vector scope screen represents the saturation or intensity of the color. The angular position of the color dots represents the hue or tint of the color. If there are color dots missing, or if the color dots are shifted away from a normal vector position, then the color process stage or its support voltages are likely to be at fault. The encoder IC is the final stage in forming the NTSC color signal. Within the encoder stage, the R-Y and B-Y input signals are used to amplitude modulate 2 separate 3.58 MHz frequencies. These 2 outputs are combined and then mixed with the color burst signal to produce the NTSC color signal. The resulting color signal can be seen as only having the chrominance and burst signal components. The Y and sync signals are mixed with the color information to form the video signal. The complete video signal reflects the added luminance and sync pulse signals. The encoder stage depends on 3 support signals and an EVR control voltage in order for the color sections within to function. Therefore, if the color signal is missing or lacks the color burst signal, the encoder or its support signals and voltages are likely to be at fault. So how can we determine if a color problem is due to a failure in the color process stage itself, the encoder stage and its supports, or EVR misadjustments? To answer this question, first analyze the picture on the monitor and the pattern on the vector scope while shooting a color bar chart. Each color can be easily identified by blocking the individual colors on the chart. Also, look for color dots which are missing from the boxes on the vector scope, dots which are shifted out of position or low in amplitude, and try to determine if there is a problem with a specific color. For example, if red is missing, you should check the red signal flow to the color processing stage and the red processing circuits in the encoder stage. When checking the color process stage, check each input signal to determine if the preceding stage is operating normally. If okay, check the output of the color process stage. If not correct, check the support voltages for this stage, including the DC offset or the EVR signals. EVR misadjustments can also cause color defects. If an EVR-controlled signal is out of spec, adjust it with the RM95. In this example, the R-Y U adjustment is out of alignment. Adjust it until correct. If the camera circuits were grossly misadjusted so that adjustment is impossible, enter the initial EVR settings as outlined in the service manual. An entire camera alignment must then be performed, however, to properly align the camera. Initial settings should only be used in extreme misalignment situations. In our previous discussion, we illustrated how the CCD output signal is separated to S1, S2, and Y signals. The Y signal output from the signal separator circuit is also input to the color matrix and also to an external delay circuit. The S1 and S2 signals are processed internally to produce the YL-YH signal or vertical aperture. This signal increases picture detail and horizontal resolution. The S1 and S2 signals are also combined with the delayed signal to produce the YH signal. The YH signal and the vertical aperture signal are output to the encoder stage. The YH signal is first sent through a small delay line. This process generates the horizontal aperture signal, which increases vertical resolution and picture detail. The YH, horizontal aperture, and vertical aperture signals are combined within the encoder IC. Within the encoder IC, the YH signal goes through several internal EVR-controlled correction circuits. These circuits set the level and clean the blanking area. It is then mixed with the on-screen character display and sync signals. They are combined externally with the color signal from the mixer to produce the NTSC video signal. YH signal problems are easy to identify. If the YH signal was missing, it would cause the color picture to appear pale due to the lack of brightness picture information. This symptom can also be identified by the loss of the white color bar display on the monitor screen and by a chroma-only signal at the output. Therefore, if there is a YH signal problem, the encoder stage and its support signals and voltages are likely to be at fault. Our 8mm troubleshooting journey is now complete. In Tape 2 of this program, we explored the camera section of an 8mm camcorder. We examined the power on sequence. and how to inspect focus and white balance for proper operation. We also explained how the iris and AGC control brightness and how the video process circuits work. Now you are ready to take the wheel and drive the road to successful 8mm troubleshooting.